In this screencast, we're going to look at interpreting the reduced row echelon form in terms of system solutions and linear combinations. We got three different systems here, and first we want to just review what does it mean to be in reduced row echelon form. To be in reduced row echelon form, every row needs to start with a leading one. I'll circle the leading ones to begin with. These leading ones need to march down to the right. In other words, a leading one in a row has to occur further to the right than a leading one in a previous row. They don't have to follow exactly a diagonal pattern. As you see down here, it skips a column. That's okay as long as the leading ones just occur to the right. Any row of zeros must always occur at the bottom of your matrix. You may not have a row of zeros, but if it occurs, it's got to be at the bottom. And then last, any leading one needs to be, it's in a pivot column, and this place where that leading one is called a pivot. Above and below each pivot needs to be entirely zeros. So notice above and below all the pivots we have zeros. That makes that means that the matrix is in reduced row echelon form. Now we're going to interpret in terms of systems. When we interpret it in terms of systems, there are essentially equal signs that we left out here that I'm going to put back in. When I put it in terms of equal signs, then the reduced row echelon form over here tells me that, this says x equals 2, y equals -1, and z equals 3. In other words, if this is an equation of three equations with three unknowns, it's a system of equations with three equations and three unknowns, then we have a solution, a unique solution to -1, 3. Well, look at the next one. This one tells me that x equals 0, y equals 0, and then down on the bottom I have a 0x plus 0y equals 1. 0 equals 1. Well, that's absurd, which means there is no solution. And down now on the last one, we have, I'm going to rewrite this as, we have 4 variables here. So if you think of this, you've got 4 equations, 4 unknowns. We need to give the unknowns names. I'll call them x1, x2, x3, x4. So here what we have is we've got x1 plus 2x3 equals 1. We've also got x2 minus x3 equals 2. And then on this row I have x4, let's skip a spot for a second, x4 is -3. Because x3 was a non-pivot column, I'm going to just, we'll call it a free variable, and I'm going to write the equation x3 equals x3 in. The reason I did that is now I can solve for the variables x1, x2, and x3. Notice that I can write all these variables in terms of the variable x3. So let's just do that. x1 is 1 minus 2x3, x2 is 2 plus x3, and x3 is x3, and x4 is -3. I'm going to now write it in matrix form, x1, x2, x3, x4 equals, let's take the constants, the 1, the 2, there's no constants here, and a -3. Now let's take all the things that are multiplied by x3. We've got a -2, we've got a 1, we've got a 1, and then there's nothing here. This is our system's solution. There are actually infinitely many solutions, and you can pick x3 to be any number you want and get another solution. So this is an example of a system with infinitely many solutions. Alright, that takes care of the interpretation in terms of solutions to systems. Now we're going to look at linear combinations. What does RREF tell us about linear combinations? We're going to look here at linear combinations of columns. So here I have 4 columns. Are the columns linearly dependent or linearly independent? Well, since the 4th column is not a pivot column, I know the 4th column, this 12, 7, -8, is actually a linear combination of the ones that preceded. So I'm going to write 12, 7, -8. And then I'm going to form it as a linear combination of the vectors 2, 0, 2, 1, 5, 6, and 3, 4, -2. And the numbers in the reduced row echelon form tell me precisely the coefficients to use when I create my linear combination. So these are the coordinates of 12, 7, -8 relative to the pivot columns. And if you just check 2 minus 1 plus 9 is 12. Or sorry, 4 minus 1 plus 9 is 12, and you can check the rest as well. Non-pivot columns can be written in terms of the pivot columns using the coefficients in RREF. When I look at this one, every single column contains a pivot, which means they are independent columns. None of them can be written as a linear combination of the others. Now we'll come down to the bottom. On this bottom one, we have two non-pivot columns. We've got the third column and the fifth column that are non-pivot columns. So I'm going to take the 2, 6, 7, 4, and I'm going to write that as a linear combination of the columns that preceded. So let's write down the 1, 2, 4, 2, and the 0, negative 2, 1, 0. And we're going to use these numbers, 2 and negative 1, and then we'll just check. 2 minus 0 is 2, 4 plus 2 is 6, 8 minus 1 is 7. That is exactly how I can write this column as a linear combination of those. Let's now do the last column, the negative 8, 1, 6, negative 4. Well, I know I can write that as a linear combination of the first, second, and third columns using 1, 2, and negative 3 as its coordinates. So I'm going to write 1, 2, 4, 2, 0, negative 2, 1, 0, 3, negative 1, 0, 2. Now I need to include the numbers 1, 2, minus 3. Sum them up, and 1 plus minus 9 is negative 8. 2 minus 4 plus 3 is 1. Check if that works. I'll let you check the rest. That completes the screen cap.